September 1943. The humid air of Rabaul hung heavy as Lieutenant Commander Takeshi Yamada knelt beside the twisted wreckage of an American bomber. The B-25 Mitchell had gone down 3 days earlier over New Britain, its crew killed on impact. What interested Yamada wasn't the aircraft itself. Japanese intelligence had examined plenty of American bombers. What interested him was the equipment scattered across the jungle floor. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Among the debris, still strapped to what remained of the radio operator's station, sat an olive-drab metal case, roughly 2 feet tall, a foot wide, sealed with latches. American markings were barely visible through mud and impact damage. SCR-300. Signal Corps Radio, number 300. Yamada had spent 6 years with the Imperial Japanese Navy's Communications Research Division before the war. He understood radio technology intimately. He knew Japan's military radios, their capabilities, their limitations. He also knew from intelligence reports that American forces were using portable radios at the company and battalion level, something no other army in the world had achieved, including Japan. The recovery team loaded the radio onto a transport aircraft bound for Tokyo. It would take 2 weeks to reach the technical research facility at Meguro, but Yamada travelled with it, unable to sleep, his mind cataloguing questions. How were the Americans producing portable radios in such quantities? More importantly, how were they achieving ranges that seemed impossible given the power limitations of battery-operated equipment? Japan had Type 94 radios, backpack sets that theoretically gave infantry units mobile communications. But they were heavy, temperamental, and their range barely exceeded 1 mile under ideal conditions. American forward, observers were calling artillery strikes from distances Japanese sets couldn't even dream of achieving. Meguro, located in southern Tokyo, housed Japan's primary military communications research center since the early 1930s. Here, in laboratories staffed by engineers from Nippon Electric Company, Hitachi, and Toshiba, technicians evaluated everything from basic field telephones to experimental radar systems. The facility occupied several nondescript buildings that from the outside appeared to be ordinary warehouses. Inside, however, precision instruments filled every available surface: oscilloscopes, signal generators, frequency analyzers, the tools needed to understand electronic warfare. When the SCR-300 arrived on September 28, 1943, a team of 12 engineers and technicians stood waiting. Professor Hiroshi Nakamura, the facility's technical director, circled the damaged radio slowly, notebook in hand. Nakamura had designed and components for Japan's naval communications systems, equipment so carefully engineered that production required skilled craftsmen working with precision tools. He reached out, running his fingers along the SCR-300's steel case. The welds were rough, clearly mass-produced. The construction showed none of the refined manufacturing that characterized Japanese military equipment. This was industrial assembly, quantity over artistry. But Nakamura was a scientist first. His job wasn't to judge aesthetic quality. His job was to understand how this radio worked, and more critically, why American forces were winning the communications war. Over the next 3 weeks, his team would dismantle this radio component by component, test every circuit, measure every specification. They would attempt to replicate its performance using Japanese manufacturing methods. The findings, everyone suspected, would be forwarded directly to the Army and Navy ministries, to men desperately trying to maintain Japan's war production as American submarines strangled supply lines and strategic bombing began its terrible work. No one present that humid September morning could have predicted what they would discover, or how fundamentally it would challenge everything they understood about radio engineering, industrial production, and the nature of the war Japan was losing. The disassembly began on September 30th, 1943, under harsh electric lights that turned the laboratory into a theatre of revelation. Yamada led the radio frequency analysis team, while Nakamura supervised structural examination. A third group, led by civilian engineer Kenji Matsumoto from Nippon Electric Company, would evaluate manufacturing methods and component sourcing. 3 perspectives, 1 goal: understand how America was winning the war of communications. Matsumoto examined the external case first. Steel, approximately 3 mm thick, spot-welded at the seams. The construction was crude by Japanese standards. Japanese military equipment used carefully fitted joints, often brazed or precision-welded to ensure water resistance and electromagnetic shielding. The SCR-300's case showed none of this refinement. Yet, when Matsumoto tested the seals, he found them perfectly adequate. The radio was weatherproof, mechanically sound, and clearly designed for rough handling. "They built this for soldiers who don't care about their equipment," Matsumoto said, making notes. "Not for specialists who maintain it carefully." Nakamura disagreed initially. "Carelessness is inefficiency. Every gram of excess material is wasted. Every loose tolerance is potential failure." But as they continued the examination, his perspective would shift. The power supply told its own story. Matsumoto removed the battery compartment and found something unexpected. 3 separate battery packs, BA70, the standard configuration, providing different voltages for different circuits. 4.5 volts for tube filaments, 90 volts for the receiver plate circuits, 150 volts for the transmitter. This is extremely inefficient. One of the younger engineers, Hiroshi Tanaka, fresh from Tokyo Imperial University, observed, "Why use 3 different voltages? Our Type 94 uses a single battery pack with taps for different circuits. More efficient, lighter weight." Yamada held up the American battery pack, examining the construction. "Look at the terminals. Simple screw connections. Look at the casing. Standard sizes, probably commercially produced. These aren't custom military batteries manufactured to special specifications." These are batteries they can produce anywhere, using civilian manufacturing equipment. 1 design, multiple applications, 1 supply chain. The Type 94's custom battery packs required specialized production facilities. They used hand-wound cells, carefully assembled to military specifications that civilian factories couldn't meet. This meant limited production capacity, constant supply problems, and field units that couldn't jury-rig replacements when official supplies failed to arrive. The Americans had built their radio around batteries that any industrial facility could manufacture. It wasn't elegant engineering, it was practical engineering, and the difference was becoming increasingly apparent. The antenna examination came next. The SCR-300 used a collapsible steel antenna, approximately 6 feet when fully extended, mounted on a flexible base that allowed it to bend without breaking. Japanese Type 94 antennas used rigid steel construction. Superior signal characteristics theoretically, but they broke constantly in combat. Field reports documented countless instances of broken antennas rendering sets useless. The American antenna, by contrast, was designed to survive abuse. The flexible mount absorbed impacts. The segmented construction allowed partial operation even if sections were damaged. When Tanaka tested the antenna in the facility's radio frequency chamber, he found something remarkable. "Professor Nakamura," he called out, "the antenna efficiency is actually quite good. Not optimal, but well within acceptable parameters for military voice communications. The flexible mount introduces some signal degradation, but the trade-off in durability appears worthwhile." Nakamura examined the data. Japanese engineers optimized for maximum performance. The Americans had optimized for survival. In laboratory conditions, Japanese design won. In combat conditions, with mud, rain, and soldiers who weren't radio specialists, American design worked when Japanese design failed. October 2, 1943. The team began the delicate process of removing the radio's internal components. What they found inside challenged everything they understood about vacuum tube circuit design. 18 tubes, miniature versions, approximately the size of a medicine bottle. Japanese military radios used standard-sized tubes, carefully selected for performance characteristics. These American miniature tubes looked almost toy-like by comparison. Yet when Yamada tested them individually, he discovered they performed remarkably well. More importantly, they were rugged. He subjected sample tubes to shock testing, dropping them from increasing heights onto concrete. Japanese tubes typically failed after drops of 1 meter or less. The American tubes survived drops of 2 meters or more. "How is this possible?" Tanaka asked. "Vacuum tubes are fragile by nature. The filaments, the glass envelopes, they cannot withstand such impacts." Yamada examined a tube under magnification. "Look at the filament support structure. Multiple anchor points, spring-loaded mounts. They've engineered mechanical suspension into the tube itself, and the glass envelope is thicker than our standard tubes, which increases weight, slightly but dramatically improves impact resistance." This was the pattern emerging. American engineers sacrificed theoretical performance for practical durability. The circuit board layout revealed similar philosophy. Japanese radio circuits used point-to-point wiring, each connection soldered individually by trained technicians. Beautiful work, precise, but slow to manufacture and difficult to repair in the field. The SCR-300 used a different approach. Components mounted on a metal chassis with standardized spacing. Wiring ran in organized bundles with color-coded insulation. Any technician could follow the circuit paths visually without consulting complex wiring diagrams. "This is designed for field repair by ordinary soldiers," Nakamura said slowly, understanding dawning, "not for factory specialists." According to documents recovered with the radio, American technical manuals assumed that maintenance would be performed by personnel with minimal electronics training. The manuals included step-by-step troubleshooting procedures with simple voltage measurements and component replacement instructions. Japanese maintenance documentation assumed trained specialists with access to sophisticated test equipment. Matsumoto spent 3 days examining the manufacturing marks on individual components. His findings were disturbing. The resistors came from multiple manufacturers: Allen Bradley, International Resistance Company, Omite. The capacitors similarly showed varied sourcing: Cornell Dubilier, Sprague, Aerovox. This wasn't normal military practice. Japanese military radios used components from approved manufacturers, often single-sourced to ensure consistent quality. "They are building these radios with components from their commercial electronics industry," Matsumoto reported during the daily briefing. "Multiple suppliers, standardized specifications, interchangeable parts. This is mass production methodology applied to military equipment." Implications were staggering. Japan's military electronics production relied on specialized facilities, producing custom components to unique specifications. This created bottlenecks. When a facility was damaged by bombing or supply problems arose, production stopped. The Americans had designed a radio that could be built anywhere, using components available from dozens of sources. If one supplier failed, others filled the gap. The system was resilient in ways Japanese manufacturing could never match. October 7, 1943. The frequency modulation circuitry became the focus of intense study. Japanese military radios used amplitude modulation, AM, the standard since radio's invention. Every radio engineer in the room had been trained in AM theory and practice. The SCR-300 used frequency modulation, FM, a relatively new technology that Japan had not widely adopted. Yamada understood FM theoretically, but seeing it implemented in portable military equipment was different. Professor Nakamura invited Dr. Takeshi Okabe from Tokyo Imperial University, one of Japan's few FM specialists, to consult. Okabe arrived on October 9th and spent 2 days analyzing the SCR-300's FM circuits. His assessment, delivered to the assembled team on October 11th, was sobering. "Gentlemen, Okabe began. Frequency modulation offers several significant advantages for military voice communications. First, FM is naturally resistant to interference from electrical equipment, vehicle engines, artillery fire, all the noise sources that plague AM communications on the battlefield. Second, FM provides superior audio quality, meaning messages are understood more clearly even in difficult conditions. Third, FM's capture effect means the strongest signal on a frequency dominates, reducing confusion from multiple transmitters. He paused, letting this sink in. The Americans have implemented FM in a portable military radio that every infantry company possesses. This gives them communication clarity that our forces cannot match. Tanaka asked the obvious question. Can we replicate this design? Can we build FM radios for our own forces? Okabe's expression was grim. Technically, yes. But consider what implementation requires. FM circuitry is more complex than AM. It requires precision components, stable oscillators, discriminator circuits that are difficult to manufacture. The Americans are producing these by the thousands. Our industry lacks both the specialized components and the production capacity. The testing phase began October 13th, 1943. The team had repaired the battle-damaged SCR-300 sufficiently to attempt operation. They installed replacement batteries, Japanese-made equivalents that approximately matched the required voltages, and powered up the unit. The radio required a 10-minute warm-up period. This wasn't surprising. Vacuum tube equipment always needed time for the tubes to reach. Operating temperature. What surprised everyone was what happened after warm-up. The radio worked flawlessly. Crystal clear audio. No static. No interference from the laboratory's electrical equipment or the city's power grid outside. FM's noise immunity was immediately obvious to everyone listening. Yamada tuned through the 41 channels, marveling at the frequency stability. Japanese Type 94 radios drifted significantly as components heated up. Operators constantly adjusted tuning. The SCR-300 held its frequency precisely, channel after channel. Automatic frequency control, Okabe explained, pointing to circuits in the receiver section. The radio continuously adjusts itself to maintain lock on the incoming signal. The operator doesn't need to touch the tuning control once communication is established. Range testing came next. The team set up a second receiving station using Japanese equipment and transmitted from the repaired SCR-300 at increasing distances. Tokyo's urban environment wasn't ideal for testing. Buildings interfered with signals. Electrical interference was constant, but even under these difficult conditions, the SCR-300 achieved remarkable range. At 3 miles, the signal remained strong and perfectly clear. At 5 miles, still usable, though beginning to fade. At 7 miles, weak but still intelligible. The Japanese Type 94, tested for comparison, achieved barely 1 mile of reliable communication under the same conditions. At 2 miles, the signal was virtually unusable. The Americans were achieving 5 to 7 times the effective range of Japanese equipment, with similar power output and similar frequencies. The difference wasn't power. The difference was frequency modulation's efficiency and the radio's superior circuit design. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Nakamura wrote in his report that evening, "The enemy has not built a superior radio through more powerful transmitters or more sensitive receivers. They have built a superior system through better modulation methods, more practical design philosophy, and manufacturing approaches we cannot duplicate. This radio represents American industrial thinking, not American electronic innovation. The innovation lies in making sophisticated technology producible at scale." October 17th, 1943. The metallurgical analysis began. Professor Ichiro Suzuki arrived from Tohoku Imperial University, a specialist in materials science and manufacturing processes. His job was to determine whether Japan could physically manufacture SCR-300 components using available materials and industrial capacity. The steel case analysis came first. Suzuki examined samples under microscope and subjected them to stress testing. Medium carbon steel, he announced. Nothing special about the alloy. Composition. Quality is good, but not exceptional. However, the forming process is interesting. These panels were stamped in high-volume presses, probably producing hundreds per day. The welds are spot-welded using semi-automatic equipment. He pulled out reports on Japanese military electronics manufacturing. We use hand-fitted cases, individually brazed seams, artisanal methods that produce superior weatherproofing but require skilled metal workers and significant time per unit. The Americans have sacrificed some weatherproofing quality for production speed. Their cases are adequate, not perfect, but they can produce 10 for every one we manufacture. The vacuum tube analysis proved even more revealing. Suzuki disassembled several of the miniature tubes, examining the internal construction. These tubes are mass-produced using automated assembly equipment, he explained. The filament supports are stamped metal. The pin connections use standardized spacing. The glass envelopes are machine-formed, not hand-blown. Every aspect of construction prioritizes high-volume manufacturing. Japanese vacuum tubes used hand-assembled internal elements. Skilled glassblowers formed the envelopes. Each tube received individual quality inspection. This produced excellent tubes but limited production capacity. During 1942, Japan's entire vacuum tube production for military applications totaled approximately 2 million units. The United States produced over 100 million vacuum tubes that same year, most for military applications. The difference wasn't just industrial capacity, it was industrial philosophy. Japan built tubes as precision instruments. America built tubes as consumable commodities. Matsumoto compiled the most damning evidence. He had been cataloguing every component in the SCR-300, cross-referencing with Japanese industrial capability. On October 20th, he presented his findings to the assembled team. "Gentlemen," he addressed them. "Formally, I have identified 43 different component types in this radio. Of these, we can manufacture 31 using existing Japanese industrial facilities. 12 components we cannot produce at all without significant retooling and development work." He consulted his notes. "The miniature vacuum tubes require automated assembly equipment we do not possess. The precision resistors need wire drawing capabilities beyond our current manufacturers. The variable capacitors use materials we cannot source reliably. The quartz crystals require growing and cutting precision we have not mastered at scale." The room fell silent. Yamada spoke carefully. "Are you saying we cannot build equivalent radios?" "I am saying," Matsumoto corrected, "that we cannot build equivalent radios in equivalent quantities. We could produce small numbers through intensive effort and by hand-selecting components from limited production runs. But the Americans are producing these radios by the thousands. We lack both the component supply chain and the assembly capacity to match their production volume." Professor Nakamura stared at the disassembled SCR-300 components spread across the laboratory benches. Each piece represented choices, deliberate engineering decisions that prioritized production speed, supply chain robustness, and field maintainability over technical perfection. The Americans hadn't built better radios through superior electronics theory. They'd built a better radio system through superior industrial organization, and Japan was losing to that system. October 23, 1943. The team prepared for the most critical evaluation, operational doctrine comparison. How were American forces using these radios, and how did that compare to Japanese communications doctrine? Captain Yoshiro Taniguchi arrived from Imperial General Headquarters to participate in this phase. Taniguchi had served as communications officer during the Guadalcanal campaign, experiencing firsthand the communications challenges of jungle warfare. The briefing began with basic organizational facts. American infantry companies each received one SCR-300 operating in the battalion command net. Battalion headquarters received multiple sets for coordination with regiment and with subordinate companies. Every American infantry battalion possessed instantaneous voice communications from company level to regiment. Captain Taniguchi absorbed this information with visible frustration. "Our companies have no radios at all," he said flatly. "Battalion headquarters might have one Type 94 if we're fortunate, but effective range is so limited that the set is often useless. Most of our tactical communications rely on runners or wire telephone lines that are constantly cut by artillery fire." Yamada had compiled intelligence reports about American radio operations during the Solomon Islands campaign. According to captured documents and prisoner interrogations, American forward observers use SCR-300s to call artillery support directly. They report enemy positions in real time, adjust fire corrections immediately, and achieve time from target identification to artillery impact measured in minutes. Taniguchi nodded grimly. "I witnessed this at Guadalcanal. American artillery response time was extraordinary. We assumed they had pre-registered fire plans. Now I understand they were simply communicating more effectively than we thought possible." The tactical implications were devastating. Japanese infantry attacks relied on surprise and speed, attempting to close with American positions before supporting fires could be brought to bear. But American forces with SCR-300 radios never lost communication with their artillery. Forward observers moved with the infantry, maintaining constant contact with fire support coordination centers. Japanese attacks that should have achieved surprise found themselves under accurate artillery fire within minutes of detection. The coordination advantage extended beyond artillery. Tank infantry cooperation, medical evacuation, ammunition resupply. Every aspect of modern warfare that required communication worked better for American forces. Not because their doctrine was superior, but because their communications actually functioned when Japanese communications failed. "We are fighting with one hand tied behind our backs," Taniguchi said quietly. "Every tactical decision we make assumes communication will fail, runners will die, units will become isolated. The Americans assume communication will succeed. That fundamental difference shapes everything from attack formations to defensive positioning." Nakamura added technical perspective. "The frequency modulation makes enemy interception more difficult as well. Our intelligence units monitoring American radio traffic report that FM signals are harder to detect and much harder to decrypt than AM signals. The Americans gain operational security along with communication clarity." The discussion turned to production numbers. Intelligence estimates suggested the United States had produced at least 15,000 SCR-300 radios by mid-1943, with production accelerating. Japan's total production of Type 94 radios since 1941 totaled approximately 3,000 units, and production was constrained by component shortages and manufacturing capacity limits. The Americans were outproducing Japan 5-1 in portable military radios, but the gap was even wider because American radios worked reliably, while Japanese radios frequently failed. A force multiplier effect made the disparity even worse than production numbers suggested. Matsumoto performed a calculation. "If we assume American radios achieve 5 times the effective range of our Type 94s, and if we assume their reliability is twice as high, and if we account for their 5-1 production advantage, then the effective communications superiority is approximately 50-1. He let that number hang in the air. For every one functioning Japanese radio communication, American forces achieve 50 successful transmissions. The room was silent. These men were engineers and scientists, accustomed to solving technical problems through analysis and innovation. But this problem couldn't be solved through better engineering. This was a systemic industrial gap that no amount of technical brilliance could close. Japan lacked the raw materials, the manufacturing capacity, the component supply chains, and most critically, the time to build equivalent systems. October 28, 1943, dawned cold and grey. Professor Nakamura had spent sleepless nights drafting the technical assessment report. The document would go to the highest levels of military command, to men who needed to understand why American forces were achieving tactical superiority in communications. The report needed to be honest, even if that honesty was painful. The final testing session focused on durability and maintenance. The team had repaired the battle-damaged SCR-300 as much as possible, but combat had taken its toll. Several vacuum tubes were cracked, the case was dented, internal wiring showed stress damage, yet with replacement batteries and replacement tubes, the radio still functioned. Yamada conducted the maintenance evaluation. Using the captured American technical manual, translated into Japanese, he attempted to perform standard field maintenance procedures. The manual assumed the operator had basic mechanical aptitude but no specialized electronics training. It provided step-by-step instructions with clear diagrams. Replace defective tubes, Yamada read aloud, following the procedure. Remove the back panel using screws at 4 corners. Locate the defective tube using the voltage table in Appendix C. Remove tube by pulling straight out from socket. Install replacement tube, ensuring pins align with socket holes. Replace back panel and secure screws. He completed the tube replacement in 7 minutes. No special tools required, no complex adjustments needed. The radio resumed operation immediately. For comparison, servicing a Japanese Type 94 radio required specialist training. The technical manual assumed operators had advanced electronics knowledge. Field repairs often required returning equipment to depot-level maintenance facilities. The Americans have democratized radio maintenance, Yamada reported. Any soldier with basic intelligence can perform repairs that would require trained specialists using our equipment. This means their radios stay operational in the field, while ours require evacuation for service. The psychological dimension proved equally important. Soldiers who trusted their equipment used it effectively. Japanese infantry had learned through bitter experience that Type 94 radios were unreliable. Batteries died quickly. Components failed constantly. Units stopped depending on radios and reverted to traditional runner-based communications. American soldiers, by contrast, trusted their SCR-300s. Intelligence reports and prisoner interrogations consistently described American confidence in radio communications. Forward observers knew their calls would get through. Company commanders knew battalion would receive their situation reports. This psychological advantage was impossible to quantify, but undoubtedly affected tactical effectiveness. Nakamura compiled all findings into the assessment report. His conclusions were methodical, scientifically supported, and devastating. The SCR-300 represented American industrial philosophy applied to military communications. Frequency modulation provided superior performance. Mass production methods enabled overwhelming numerical superiority. Practical design philosophy ensured field reliability and maintainability. Standardized components created resilient supply chains. Every aspect of the system prioritized operational effectiveness over technical elegance. Japan's Type 94 radios, by contrast, reflected different values. Artisanal manufacturing methods produced limited quantities. Amplitude modulation used familiar but inferior technology. Complex maintenance requirements reduced field availability. Custom components created fragile supply chains. The radios performed adequately when they worked, but they worked too infrequently and in too few numbers to matter strategically. The Americans have not achieved a breakthrough in radio theory, Nakamura wrote. The underlying principles are well understood. What they have achieved is a breakthrough in industrial organization and production philosophy. They identified what soldiers actually needed in the field, designed equipment that met those needs adequately rather than perfectly, and manufactured it in quantities that ensure availability. We designed equipment that meets theoretical ideals, manufacture it in limited quantities, and wonder why soldiers prefer runners to our radios. November 1st, 1943. The Imperial Japanese Army and Navy Ministry received Nakamura's assessment. The report was classified secret, distributed to fewer than 20 senior officers and civilian officials. Lieutenant Commander Yamada was ordered to brief selected staff officers on the technical findings. The briefing room at Army Ministry headquarters was austere: wooden floors, plain walls, a single table surrounded by officers whose expressions ranged from skeptical to hostile. Yamada understood their resistance. He was about to tell them that enemy equipment was superior and that Japan couldn't match it. These were not messages military officers wanted to hear. He began methodically, presenting technical specifications without editorial comment. The SCR-300's frequency range, its 41 channels, its effective communication distance of 3 to 5 miles, its frequency modulation system. He showed comparison data with the Type 94, range, reliability, maintainability, production numbers. Every metric favored the American radio. General Yoshio Sato, responsible for Army communications procurement, interrupted. These ranges you cite, 3 to 5 miles, are laboratory measurements, correct? Not field performance under combat conditions? Yamada had expected this challenge. General, the ranges I cite come from American field manuals that explicitly state expected performance under combat conditions. These are not theoretical maxima. These are distances American forces routinely achieve in actual operations. Our own intelligence reports from multiple theaters confirm these capabilities. He presented intercepted radio logs from Guadalcanal, New Georgia, and New Guinea, American forward observers calling artillery strikes from distances where Japanese radios couldn't function, tank infantry coordination across dispersed formations, medical evacuation requests transmitted from deep in jungle terrain. The evidence was overwhelming. Colonel Masahiko Fujimoto, an infantry officer with Guadalcanal combat experience, spoke quietly. I have witnessed American artillery response times, minutes from target identification to accurate fire. Our artillery takes 30 to 40 minutes minimum, often longer. We attributed this to superior American artillery equipment. Now I understand their communications enable their artillery to be effective. The discussion turned to production capacity. Could Japan manufacture equivalent radios if industrial resources were allocated? Matsumoto, present as civilian technical advisor, addressed this directly. Honorable officers, Japan currently produces approximately 200 Type 94 radios per month. This production rate is constrained by component availability, not by assembly capacity. To match American SCR-300 production, we would need to manufacture approximately 2,000 radios per month. He paused for emphasis. This would require vacuum tube production to increase tenfold, which is impossible given current industrial capacity. It would require precision resistor and capacitor production to increase similarly. It would require quartz crystal production that we currently lack entirely. Even if we converted all available electronics manufacturing to military radio production, we could not achieve American production volumes. General Sato's response was sharp. Are you telling me our industrial capacity is inadequate? I am telling you, Matsumoto replied carefully, that American industrial capacity is extraordinary. They outproduce us in virtually every category of military equipment: radios, aircraft, ships, vehicles, ammunition. This isn't unique to communications equipment. This is systemic industrial superiority, the briefing concluded, after 3 hours. No decisions were made. No policies changed. The officers filed out, some thoughtful, others clearly unconvinced. Yamada remained behind with Professor Nakamura, who had observed silently throughout. Will anything change? Yamada asked. Nakamura's expression was somber. No, we lack the resources to change even if leadership accepted our findings. Japan is fighting with pre-war industrial capacity, while America mobilizes the world's largest industrial economy. Technical assessments cannot close that gap. November 7th, 1943. Orders arrived from Army Ministry. The captured SCR-300 was to be destroyed. Enemy equipment could not be allowed to fall back into Allied hands as American forces advanced across the Pacific. Security regulations required complete destruction of all examined enemy technology. But before demolition, Nakamura requested permission to document the radio photographically for archival purposes. Permission granted. The photography session took 2 days. Every component, every circuit, every mechanical detail captured on film. These images would survive, preserved in Japan's technical archives, a record of American industrial and engineering achievement during the war. The SCR-300 was destroyed on November 12, 1943, by thermite charges that melted the radio into unrecognizable slag. But Nakamura's assessment survived, filed away in military archives, a testament to Japanese technical honesty, even in defeat. The report made clear that superior American radio communications stemmed not from brilliant inventions, but from systematic industrial advantages that Japan simply could not match. Yamada returned to communications research, spending the rest of the war attempting to improve Type 94 reliability with limited success. Component shortages worsened as American submarines cut supply lines. Manufacturing quality degraded as skilled workers were conscripted. By 1945, Japanese military radio production had essentially collapsed. Professor Nakamura survived the war. In 1947, during the American occupation, he encountered American Signal Corps officers installing radio communications systems for Japan's reconstruction. The equipment included SCR-300s, still in service 2 years after war's end. He introduced himself, explained his wartime analysis of their radio, and shared his assessment report, now declassified. The American officers were fascinated. One of them, a Major William Reynolds, later wrote in his memoir about meeting the Japanese engineer who had so thoroughly studied American radio technology. "He understood our equipment better than most of our own soldiers," Reynolds wrote. "He saw clearly what we had achieved, not through better science, but through better organization. He paid us the compliment of honest analysis, even though that analysis documented his own nation's defeat." Later, military historians would recognize Nakamura's report as one of the most insightful analyses of World War II industrial warfare produced during the conflict. Written with scientific objectivity and painful honesty, it explained not just why Japan lost the communications war, but why America won through systematic thinking, industrial efficiency, and design philosophy that prioritized practical effectiveness over theoretical perfection. The final entry in Nakamura's research log, written November 10, 1943, captured his understanding. "We examined the SCR-300, expecting to find inferior technology we could dismiss. We found instead a superior system we could not replicate. We sought confirmation of our engineering traditions. We found instead explanation of our inadequacy. The Americans built the correct radio for industrial warfare. We built precision instruments for a war that required tools, not artwork. History will remember which approach succeeded." Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.